So, good morning, everyone. Today I will be presenting our study. My name is Anastasiia Mozghova and I'm co-author. I'm from the Shevchenko National University of Kyiv. So, the topic of our study is personal name disambiguation in news articles, a hybrid method for enhancing entity resolution in Russian-Ukrainian war coverage. So, let's start. First of all, entity resolution is vital in NLP. It aims to link all mentions of link entity all entities that refer to one a real world entity. It is vital because it reduces ambiguities in and identity mentions. It is essential for reliable text analysis, large-scale data processing, and information retrieval. So commonly faced challenges in this field are name variations, spelling mistakes, and transliterations. We face them all in our study. Different methods are applied in this field of study, but it is worth mentioning that some of them are often created for domain-specific texts. Let's proceed. Speaking more about approaches, entity resolution has been studied for over 60 years and different approaches were created and applied, but the commonly used ones are string-based, like TF-IDF, back of words, and what we used are is the Morel-Levenstein distance. They lack context and considered to be less accurate. Clustering techniques, they are scalable but computational expensive, and as string-based techniques lack context. Supervised models are accurate but require large label datasets, and that is a problem because for each text, we would need such label dataset, and well, again, domain specific, it is tough, and for each task we would need to create such label datasets. Also, embeddings are used and deep learning is used. It is embeddings especially, they improve result but struggle with out of vocabulary names if we use word embeddings because word embeddings models are trained on huge text, but these texts should have these entities that we are trying to get vector for, but not all of them saw them in training data. And the last but not the least, using large language models, scientists say that it is promising, but domain sensitive, costly, and actually need careful tuning. From our personal experience, we can say that prompt should be engineered really carefully. So let's proceed. So the problem was that the dataset that we were working had many personal names that appeared in inconsistent forms, many name variations of one entity, real-world entity, and we decided to, as we wanted to improve the accuracy and the quality of our dataset, we decided to create a dictionary of personal clusters with clusters of name variations, and so we could then remove all the name variations for one name variation. So most methods applied in our study are the Morel-Levenstein distance, that is string-based approach, as we previously said, and machine learning techniques. To be more precise, deep learning techniques, we trained our own deep learning word embedding models in order to get vectors. So let's look closely in our data. So we worked with the Russian-Ukrainian war dataset. This dataset contained 16,470 unique articles. They were published by different news outlets from Ukraine, Russia, Asia, and the USA. So the interesting thing that we got 18 categories of named entities. We get them from Spacey automatically. We utilized transformer model, English transformer model to get them. And the interesting insight was that NORP GPE organization did organizations, date, and person were the most frequently used. So speaking about person-named entities, because they are in our point of view the most important, and we wanted to reduce ambiguities. We automatically extracted 15,131 named entities from RUVA articles, but some of them had multiple labels. Some of them were in possessive case, some was with at symbol, and in our point of view, that was a little bit ambiguous, and we decided to delete them. And after cleaning, we got 14,574 person name entities, and as we see, most of them appeared on news website tas.com. Let's proceed. So as we used the Morel-Wallenstein distance that was highly sensitive to symbol symbol structure and token structure, we decided to compare named entities with the same token structure, and as named entities with two token structure were the most frequently used, we decided to work with them. Let's proceed. So in our study, we applied, as we said before, two methods, the Morel-Wallenstein distance and cosine similarity. Let's look closer at them. So we used string-based matching of two token personal names. We decided to use threshold of 3 edits because it, as we discovered heuristically, it was the best one. We got the best results. This method captured typos, transliterations, spelling variations, and really good one. Speaking about the cosine similarity, for cosine similarity, we tried first of all to get a vector, get word vector from pre-trained word embedding models, fast text, word to vec, low, but we faced out of vocabulary problem, as we see on the graphic. Even one token entities didn't have vector. Most of them didn't have. And for two token personal name entities, there were no vectors at all. So we decided to train our own embedding models, and we trained it on the RUVA dataset articles. So let's proceed. So the evaluation of our methods. In order to evaluate our methods, we created manually annotated gold standard corpus. We took 500 random name variants from the set of name variants, and manually grouped them into clusters of name variants. So we had 500 name variants, and we got 539 unique individuals, and so 539 clusters. Each cluster contained name variations of one unique individual. So we utilized a macro F1, and what was interesting is that even though the Volodymyrska distance is string-based technique, it performed better because it shows that it shows macro F1 of 0096 and cosine similarity based on fast text embeddings performed a little bit worse, and we got 0.91 F1 score. So speaking about the final dictionary, that was the goal of our study. We got the final dictionary has 6,414 entries. Each entry was a cluster of variant names for one individual. So on the left side, you see the most frequent variant of among the variants of one unique person. For example, we have two name variants for Andrei Kartopalov. It was so Andrei Kartopalov and Andrei Kartopalov, and the most frequent variant among them was Andrei Kartopalov. So the interesting thing was that Volodymyr Zelensky has 22 name variations, so 22 variants of Volodymyr Zelensky, and as the statistics show to us, only 70% of clusters contained more than one variant. And therefore, mean variant per cluster was 1.3. So that's all. Thank you for listening to me. I wish you a good day. Goodbye.